Now we'll see the working of a DC generator. According to the Faraday's law of electromagnetic induction, whenever conductor is placed in a magnetic field, varying magnetic field, or conductor is moved in a magnetic field, an EMF gets induced in the conductor. So that you can observe here, there is a north and south poles in which conductor is placed and it is moving. So conductor is moving, so that can observe here like this. We can move the conductor inside the magnetic field. So these are the electromagnets, so it will produce continuous flux, and these are the conductors which are turning or which are moving in between the poles. The magnitude of induced EMF can be calculated from the EMF equation of the generator. So if the conductor is provided with a closed path, so this is a conductor and it is connected with the commutator as well as brush segment, and it is connected to the closed path. When conductor is connected to the closed path, the induced current will circulate within the path. So as I mentioned earlier, so there is a conductor, there is a commutator, there is a brushes, and through these brushes the current is allowed to flow through the external circuit or external load. So current start flowing when you provide a closed path. In a DC generator, field coils produced an electromagnetic field and the armature conductors are rotated into the field. So these are the armature conductors and field coils are placed in the poles. Thus an electromagnetically induced EMF is generated in the armature conductors. So for the information you can refer this link, so that will give the pictorial representation of DC generation. So here once again I will repeat, these are the armature conductors which are placed in between poles, and when it is rotated within the poles which are continuously producing flux like this, when the armature is rotated it will cut the flux. EMF will be induced in the armature conductors. When EMF is induced in the armature conductors, and if you provide a closed path for this EMF induced, it will start circulating current in the circuit, and these are the commutators, these are the brushes. So this brush will take the current to the external circuit. So initially the whatever voltage or current which is produced is of AC. Due to this, by using this commutator segment, this bidirectional voltage or current, it will convert into unidirectional current, that is DC. So that will be supplied at the end to the external load. Thus we will get the DC current or voltage. This is the working principle of a DC generator. Next very important topic is EMF equation of a DC generator. Consider DC generator with the following parameters: P, number of field poles; phi, flux produced per pole in Webers; Z is the total number of armature conductors present; A, number of parallel paths in armature. Each parallel path there is a specific armature conductors are placed, so this A is equal to number of parallel paths provided. N is a rotational speed of the armature in RPM, revolution per minute. Now average EMF generated per conductor. In one conductor, how much average EMF it has been generated, it is given by d phi by dt, Faraday's law of electromagnetic induction. Flux cut, rate of change of flux with respect to time, d phi by dt, that we already came across. Average EMF generated per conductor. Flux cut by one conductor in one revolution. So when conductor is rotating, so this flux cut by one conductor in one revolution, so this has to undergo how many number of poles are present, that much number of poles in one revolution one conductor has to undergo. So d phi is a flux cut by a one conductor. A small amount of flux is given by total flux into number of poles, because this conductor has to undergo the total number of poles. So it is P into phi. So d phi is equal to P into phi. Number of revolutions per second. So n is equal to RPM. N by 60 will give RPS, revolution per second, converting minutes into seconds. Therefore, time for one revolution dt. So dt 60 by n seconds. That will get as 60 by n seconds. So we have got now d phi. We have got now dt. So now we will do d phi by dt. So when you do d phi by dt, you will get p phi n by 60 volts. So now equation number 2 gives the EMF generated in one conductor. So because we are considering only one conductor here, so per conductor, so EMF induced one conductor of the generator. The conductors are connected in series with per parallel path. So that I told earlier. So if there are provided a number of parallel paths, all conductors are placed in a parallel paths. And the EMF across the generator terminals is equal to generated EMF across any parallel path. So for that reason, so P phi n z by 60a. So you have to divide by a, total number of parallel path. So n z number of conductors are present in a parallel path. So how many parallel paths are provided? In that much parallel path, this z number of conductors are present. So this average EMF induced or total number of EMF induced can be calculated as phi z np by 60a. For simplex lap winding, number of parallel path is equal to number of poles, that is a is equal to p. For lap winding, there are two types of winding that will come later. One is lap winding, second one is wave winding. If you consider the winding as lap winding, then a is equal to p, number of parallel path is equal to number of poles. So p phi nz by 60 p. So we can replace a by p because a is equal to p. So pp will get cancelled here. So only remaining is Eg, generated EMF, is equal to phi n z by 60. For wave winding, p is equal to 2 or number of parallel path is equal to 2. So number of parallel path is equal to 2. So that means to say a is equal to 2 here, or here p is equal to 2, or here a is equal to 2. So what you get is phi z np by 120. So that is very important that you have to remember. For lap winding, what is the formula for generated EMF? For wave winding, what is the formula for wave winding? Next, types of DC generators. In the DC generator, it converts the mechanical power into electrical power. The magnetic flux in the DC machine is produced by the field coils carrying current. So that already came across that field windings are wound for the poles. When current is start flowing in the field winding, it will produce a current which magnetizes the poles. So for that reason, we can tell these exciting windings or field windings are responsible for the production of flux or exciting the poles. The circulating current in the field windings produces a magnetic flux, and this phenomenon is called as excitation. In DC generator is satisfied according to the methods of this field excitation. One is separately excited DC generator. Next one is self-excited DC generators. Now we will see one by one what is meant by separately excited. In separately excited DC generators, the field windings are excited or they are given supply from the external source. If field windings are given supply from the external source or excited by the external source, then that kind of DC generator are called as separately excited DC generators. So one thing I would like to tell, even if the DC generator to produce DC voltage, initially some excitement or some exciting current or exciting voltage, exciting supply, it has to be given for the field windings first from either external source or the same source. The DC generators whose field winding or coil is energized by a separate or external DC source is called separately excited DC generator. The flux produced by the poles depends upon the field current with the unsaturated region of magnetic material of the poles. That is, flux is directly proportional to the field current. So that means to say, since the field windings are responsible for the production of flux, this flux is directly proportional to the field current IF. So if you take IF as a field current, so this flux is directly proportional to the current. So once the flux has been produced, it will increase as the current increases, it will increase, but one stage it will reaches its saturation. After that, flux remains constant. Okay, so this is called a separately excited DC generator. So these are the field windings which are excited or which are given supply externally, which is nothing to do with this generator. Only these field windings are used to energize. This will energize the poles of a DC generator. So that this is the generator. Here it has to be EG, it's not EB, it is EG. So the generated EMF EG, and this is armature resistance, which is not shown as the internal resistance. It is internally present, armature resistance RA. So this is IA, armature current. Whenever current produced by the DC generator, so this will go like this from the machine, from the generator it will go IA, it will go to the load. When load has been connected, so it will go to the load. Here IA and IL are same. Here IA is equal to IL, where IA is armature current, IL is a line current, but both are same here. The terminal voltage, the voltage which is available at the terminal, it is called as a terminal voltage. V is given by, so this is EG, it should be EG, not EB. EB is in the case of motor, is a back EMF, it will come later. EG is a generated EMF in the case of generator. EG minus IARE. So there is a drop. Wherever there is a resistance, there is a voltage drop. So since RA in internal resistance of armature is present, there is a drop, voltage drop. So this whatever EMF generated minus IARE, the voltage IARE, it will available at the terminal. So terminal voltage is equal to EG generated EMF minus IARE, that will be available at the terminal. So since once again, if we go deep and if we consider the brush contact drop, so once again the brushes, so there is a drop in the brushes when current is passing through the brushes, there is a drop in the brushes. If you consider brush contact drop, once again the voltage available at the terminal, it will be reduced. Minimum there will be two brushes, 2 into VB, voltage across brushes, voltage across brush. So total voltage available at the terminal, it will be generated EMF minus some voltage drop in the armature minus the voltage drop in the brushes. The power developed and power output is given by the equation below. So power developed, so always power is developing in the armature, the power is developing in the armature. So EG into IA, so generated EMF into armature current. So EG into IA, the power is developed in the armature. The power output, so everywhere in generator, whatever the power output is at the load side, so terminal voltage into load current. So I can write V into IL is the power output. So here IL and IA is same. So since I can write V into IL or V into IA. So next, self-excited DC generator. So here what we observed is separately excited. Now we will move on to self-excited DC generator. Self-excited DC generator is a device in which the current to the field winding is supplied by the generator itself. So that is very important thing. When the field windings are energized by the current which is produced by the generator itself, it is called self-excited DC generator. In self-excited DC generator, the field coils may be connected in parallel with the armature or in series with armature, or it may be connected partly in series and partly in parallel. So depending upon that, it is called as a shunt wound generator, series wound generator and compound wound generator. When field windings are connected in parallel with the armature, it is called as shunt wound generator. So that we can observe here, in a shunt wound generator, the field winding is connected across, that is parallel to the armature winding, forming a parallel or shunt circuit. So that you can observe here. So field windings are energized by the current which is produced by the generator itself, and it is connected in parallel with the armature winding. Therefore, full terminal voltage is applied across it. Full terminal voltage, it is very parallel to this shunt field winding. So this terminal voltage is parallel, dead parallel to the shunt field winding. So, therefore, full terminal voltage applied across it. A very small field current ISH flows through it because this winding has many turns of fine wire having very high resistance in order of 100 ohms. So what is meant by this is, in a shunt wound generators, very small amount of current is flowing through the shunt field and most of the current is flowing through the armature winding and load. Because the shunt field resistance is made up of very high resistance of very high number of turns, so very small amount of current is flowing, its value is very high, resistance value is very high, small amount of current is flowing and most of the current is flowing through load as well as armature. So ISH is equal to V by RSH, that you can see the current flowing through the shunt field resistance is I can formulate as V by RSH because this and this are parallel. So V by RSH will give ISH. The current ISH is practically constant at all loads. So armature current IA, it will be divided into two. One is ISH, one is IL. So that can observe here. So I can write IA is equal to IL plus ISH. Once again, here it has to be EG, not EB, generated EMF. And small armature resistance is present internally, which is not shown here, but internally armature resistance is present. So terminal voltage V is equal to generated EMF EG minus IRA. So just like a previous case, it is minus IA into RA. Wherever there is a resistance, armature resistance, there is a drop. So V minus IRA. So this will not come into picture. The drop across this R shunt is not coming to picture, because it is same as V. So wherever there is a series voltage drop, it will count. So V is equal to EG minus IRA. So V is equal to EG minus IRA minus 2 VB if you are considering the brush contact drop. If we consider the brush contact drop, if brush contact drop is included, the equation become minus 2 VB. So V is equal to EG minus IRA minus 2 VB. Once again, power developed is equal to EG into IA. The power is always developed in the armature, EG into armature current IA. But here, unlike in the last case, IA is equal to IL plus ISH. But the last case, this IA and IL are same. But here, IA and IL are not same, since shunt field current is present and this shunt field winding is part of this particular generator. So IA is equal to IL plus ISH here. Power output is equal to V into IL. As always, output is taken in the load side, V into IL, the power output. Next we pass on to series wound generator. Series wound generator. In series wound generator, the field coils are connected in series with the armature winding. The series field winding carries the armature current. The series field winding consists of a few turns of wire of thick wire of larger cross-sectional area having low resistance, usually in the order of less than 1 ohm. So this we can observe here. So this is a series field. It is connected in series with the armature, which has got very low resistance. ISC, IA, IL. So all currents are same. Here, since series field windings are in series with armature, and load is also in series with the armature as well as series field, only one current is present, only one circuit, only one current is present. So RSC or IA, RSC is present, IL or IA or ISC I can call. So only one current. So if you calculate the terminal voltage V, the voltage which is available at the terminal, so one drops that you can calculate. One is generated EMF, definitely V generated EMF. From this IARA drop will be there. There is a small armature resistance. There is a drop when current is flowing through that resistance. Always there is a drop. Once again, but extra drop here is RSC. So IS into RSC. So I can write since IA and ISC are same, I can take IA outside as EG minus IA into RA plus RSC. If we consider once again the brush contact drop, so there is a drop or losses, voltage drop at the brushes. Minimum 2 brushes will be present, so I can add this voltage drop also. So EG minus IA into RA plus RSC minus 2 will be. Power developed in the armature, always EG into IA, and power output V into IA. But here IA is equal to IL is equal to ISC. Next, compound wound generator. In a compound wound generator, there are two field windings. One is connected in series and another is connected in parallel. So these are the example of a compound wound generator. Here both shunt as well as series field windings are present. Once again, there are two types. One is a long shunt compound wound. Second one is short shunt compound wound. Now, what is meant by long shunt compound wound? In a long shunt compound wound generator, shunt field winding is parallel with both armature and series field. See here, you can observe here shunt field which are parallel with the armature as well as series field. So armature and series field, definitely they are in series, and this shunt field winding is parallel to both. Here the shunt field current is given by V by RSH, definitely because this shunt field is parallel with this load. This shunt field is parallel with this load, so we can calculate this RSH as V by RSH. We can calculate ISH as V by RSH. Series field current ISC is equal to IA. Series field current ISC, IA are same, but not IL. It is not equal to IL because current will be splitting here. So I can call ISC is equal to IA, that is equal to IL plus ISH. IL plus ISH. Terminal voltage, if we calculate the terminal voltage here, so this is power developed in the armature EG or generated EMF EG minus IRA voltage drop in the armature minus, once again there is a drop in the series field. Wherever there is a resistance in which current is passing, there is a voltage drop, I told earlier. So EG is equal to IRA minus IS into RSC. So this will not count because it is not in series with this line. So it is not in series with this line. So EG minus IRA minus IS into RSC. So ISC and IA are same. I can write like this. If brush contact drop is included, once again we can add minus 2 VB here. So power developed EG into IA, power developed in the armature. So it is not once again EB, it is EG, and power output is equal to V into IL. In a short shunt compound wound generators, in short shunt compound wound generator, the shunt field winding is connected in parallel with armature winding only. So we can see here the shunt field winding is connected in parallel with the armature winding. It is not in parallel with series field winding. Series field winding is in series with the load. That is one difference that you can observe. So here ISC is equal to IL Here series field current, that we can call it as same as the load, because this series field winding is in series with the load. Current passing through the series field winding and load are same, but it is not same as armature current. Shunt field current is given as ISH. Here shunt field current is given as ISH is equal to V plus ILRSC by RSH. So this is EG minus IARA by RSH. EG minus IRA by RSH, or IA is equal to IL plus ISH. Terminal voltage EG minus IRA minus IL into RSC, or minus IS into RSC, or minus IL into RSC, because these are coming in series and this is not coming to picture. If brush contact drop has been included, definitely minus 2 will be included, and power developed same as before, EG into IA, and power output power is always at the terminals, low terminals, V into IL. So this is the classification, total classification of DC generators. So that we can observe here, classification of DC machines: separately excited, self-excited, series wound, shunt wound, compound wound, and long shunt and short shunt. Next, two types of windings here. One is lap winding. In lap winding, the conductors are joined in such a way that their parallel paths and poles are equal in number. So this is the lap winding and wave winding, which are present in armature conductor, types of armature conductor winding. So these are joined in such a way that their parallel paths and poles are equal in number. So in lap winding, as I told earlier in the EMF equation of a generator, the parallel path and number of poles are equal. The end of each armature coil is connected to the adjacent segment of the commutator. So this is one armature coil. So this is one armature coil. So this is the commutators. So this is the another armature coil. So we can observe in the diagram. So each end of the armature coil, other end of the armature coil is connected to the adjacent commutator segment. So started here, commutator segment number 1, it is went like this, and other end of the coil is connected to second commutator segment. Once again same thing, the second coil, it started with the second commutator segment and end in third commutator segment. The number of brushes in the lap winding is equal to number of parallel paths, and these brushes are equally divided into negative and positive polarity. The lap winding is mainly used for low voltage, high current machines, and three types: simplex, duplex, and triplex lap windings. Next comes the wave winding. In wave winding, only two parallel paths are provided between the positive and negative brushes. Here only two parallel paths. In all conductors are placed in these two parallel paths only. Irrespective of the number of conductors present, only two parallel paths are present in wave winding. The finishing end of one armature coil is connected to the starting end of the other armature coil. Commutator segment at same distance apart. So that you can see here, the starting end is connected to the finishing end, and from here only another coil has started and it is ended here. Once again the third coil will start from here only. The finishing end of one armature coil is connected to the starting end of the other armature coil. So that is the meaning of this. In this winding, the conductors are connected in two parallel paths irrespective of the number of poles of the machine. The number of brushes is equal to number of parallel paths. The wave winding is mainly used in high voltage, low current brushes. So this is a comparison, or I can say the difference of lap and wave winding. One is, if you compare the definition, the coil is lapped back to the succeeding coil. Here wave winding, the coil of winding form a wave shape. So that you can observe in the diagram of lap and wave winding. Connection: the end of the armature coil is connected to an adjacent segment on the commutators in the lap winding, but in the wave winding it is connected to the commutator segment some distance apart. So that you can observe here. So commutator segment some distance apart. Parallel path. the number of parallel paths are equal to the total number of poles. But in wave winding, only 2 parallel paths are present. Other name for lap winding is a multiple winding, and here is called as a 2-circuit or series winding. EMF, definitely it is very less here. Wave winding EMF produces more. Here number of brush equal to the number of parallel paths. Here only 2 brushes are present. Here simplex and duplex lap windings are produced. Here progressive or retrogressive wave windings are present. Efficiency, lap winding is less, wave winding is high. Its winding cost is high in lap winding because more conductors are required, because it is taking the shape of lap, one overlapping the other. But here wave winding cost is low when compared to lap winding. Uses, as I mentioned earlier, it is used for low voltage high current machines, and wave winding is used for high voltage low current machines.